Hello friends, welcome to the molecular weight distribution and addition and the chain reaction polymerization under the edges of chemical reaction engineering in polymers. Now before we proceed further, let's have an outlook that what we discussed in the previous lecture. We were discussing about the molecular weight distribution, then discussed about the addition polymerization, radical chain polymerization, then we discussed about the overall rate of the polymerization and the gel effect in addition polymerization. In this particular chapter, we are going to discuss the thermal initiation in absence of catalyst, photoinitiation of polymerization, energetic characteristics of free radical. We will discuss about the kinetics of the chain length and then chain transfer and inhibition kinetics and dead end effect in the addition polymerization. Now let us talk about the thermal initiation in absence of catalyst, because sometimes all these reactions are proceed with the help of catalyst. So it will be easy to see that what will be the effect of the thermal initiation in absence of catalyst. So some monomers, they are known to undergo the spontaneous polymerization when carefully purified and heated in the absence of catalyst. So many other on the similar purification fail to undergo self-initiated polymerization at elevated temperature. So the addition reaction in self-initiated polymerization of pure styrene is due to the thermal activation of monomer on heating and leading to the decomposition into the radical. So some sort of the monomers, they are CO-moto once they initiated, when they heated to a specified temperature, they become the radical. So there is no need for any third party agent like catalyst. So the rate of polymerization is of second order in that particular aspect. Now, the second order dependence of Rp on styrene concentration is also indicates the rate of initiation, that is Ri, to be the second order in styrene. The initiation rates of spontaneous thermal polymerization of styrene are far smaller than those of polymerization in the presence of an initiator. So this is the basic difference. Now, the bimolecular initiation mechanism resulting in the formation of a biradical, this can be shown in this particular reaction. Now, see, when we recall this particular reaction, that is 2CH2, CHX, Ki, then radicals of CH2, CH, like this, then the rate of initiation, this Ri, can be expressed as 2Ki to the concentration of monomer to the power 2. This, if you take the things into continuation with the previous lecture, this can be represented as equation number 7. Now, considering the bimolecular termination giving rate the term of termination, so RT is equal to twice KT m to the power 2, and under steady state assumption, if we give rise to Ri is equal to RT, the chain radical concentration can be expressed as radical m is equal to Ki over Kt to the power half into concentration of m. This can be represented as equation 8. Now, the rate of polymerization Rp, this can be given as Rp is equal to Kp into concentration of m radical into concentration of m, and that is Kp is equal to Ki over Kt to the power half m to the power 2, and that is equation number 9. Now let us talk about the photoinitiation of polymerization. The photochemical reaction can also lead to initiation of free radical polymerization, and photoinitiation may be considered under three broad categories. One is the uncatalyzed, then second is the catalyzed, and third one is the sensitized photoinitiation. Let us talk about the uncatalyzed photopolymerization. So on photoactivation, the monomer M may generate excited species of M star by absorbing the quantum of the light of a specific wavelength and subsequently decompose into the radicals by homolysis or related mechanism, which then contribute to chain initiation. Like here you see that it absorbs the light and then gives the M radical, and this M radical further form this R radicals. The rate of photochemical initiation, this can be expressed by this particular equation, Ri is equal to 2,5 and Ia, where Ia is the intensity of active radiation absorbed and phi is the quantum yield of chain initiation or addition reaction, which actually stands for the number of pairs of chain radical generated per quantum of light absorbed. Now, assuming that the incident light intensity does not measurably vary with the thickness of the reaction mass. Suppose this is the reaction and this is the light intensity. So, it is independent of the reaction mass. Then Ia will be proportional to the product of the intensity of the incident light I naught. Epsilon is the molar absorption coefficient for the active radiation, and the monomer concentration is, so Ia is equal to epsilon I naught into concentration of M. This can be represented as equation 11. So if we combine this previous equation number 10 and 11, then we get this Rp value, which can be represented as equation number 12. Now let us talk about the second category, that is the catalyzed photopolymerization. In the case of photopolymerize using the photoactive additive as a catalyst or initiator in the monomer, the photoinitiator readily undergoes photolysis to generate the radicals which then initiate the chain polymerization. So if you use a simple carbonyl compound such as ketone of a general formula RCOR, the radical generation reaction showing the photolysis of the ketone, this can be represented as per this particular formula. Now, many thermal initiator which produce specific radicals on thermal homolytic cleavage of specific bond also undergo the photolytic decomposition to produce the same type of radicals. Now, the photoactivation allows the use of wide range of chemicals as polymerization initiators in comparison with the thermal catalysis process. Now, thermal homolysis occurs at a too high temperature and generally lead to the generation of a wide spectrum of radicals at various chemical bonds, and they break up randomly. Now, here if we see the rate of initiation using the photoinitiator I, this is given by Ri is equal to 2,5 epsilon I naught into I, that is equation number 13. Now, hence the under steady state and assuming the bimolecular termination, the concentration of M radical, this can be represented which 5 epsilon I naught over Kt to the power half into I to the power half. The rate of related photopolymerization is given by Rp is equal to Kp over Kt to the power half 5 epsilon I naught to the power half into I to the power half. This can be represented as equation number 14. Now, the number average degree of polymerization is usually given by the average number of monomer molecule consumed per polymer molecule. So, for evaluation of Xn from the kinetic polymerization, it is necessary to define and find an expression for the kinetic chain length and nu. Now, the kinetic chain length nu represents the average number of monomer molecule consumed by the given active center from its initiation to its termination. Now, here the kinetic chain length is viewed as a ratio of the rate of propagation Rp to the rate of initiation or to the rate of termination RT. So, these three terms are very important: rate of propagation, rate of initiation and rate of termination RT. Now, since Ri is equal to Rt, that is the rate of initiation is equal to rate of termination under the steady state condition. So, we can write that nu is equal to Rp over Ri is equal to Rp over Rt, and that can be written as equation number 15. Now, if we put the value of Rp and Rt in the equation 15, this in equation, then we get nu is equal to Kp over 2 Kt into concentration of monomer and over concentration of monomer radical. So, this can be represented as equation number 16. So, if we eliminate the radical concentration term, this m dot, then the nu can be represented as nu is equal to Kp to the power 2 over 2 Kt into concentration of monomer to the power 2 over Rp, and that can be represented as equation 17, that the kinetic chain length is inversely proportional to the chain radical concentration. So, equation 16, and hence it is also inversely proportional to the rate of polymerization. This can be represented by the equation number 17. Now, for polymerization initiated through the radical generated by the thermal decomposition of an initiator I, the equation 6 which we represented earlier, and Ri, that is equal to 2 Fkd I, this may be combined to give an alternate expression for nu. So, nu can be is Kp over 2 Fkd Kt to the power half, and then this can be concentration of m over initiator concentration to the power half. This can be represented as equation 18. Now, for purely thermal polymerization, an alternative expression of nu may be obtained by if we combine the equation 9 which we discussed previously, and Ri is equal to 2 Ki into concentration of m to the power 2. So, we get nu is equal to Kp over 2 Ki Kt to the power half. This can be represented as equation number 19. Now, let us talk about the kinetics of chain transfer. The monomer M, initiator I, and solvent S or other additive present in the polymerization system, or even the product polymer being formed, may terminate a growing radical, because once the initiation occurs, then propagation, and then it is quite obvious to get the useful property of the polymer, the chain must be terminated. So, consequently, the reacting molecule acquires a radical site which normally starts a new chain and then continues to grow at the same rate. The reactions are commonly known as the chain transfer reaction, which can be generally depicted as m dot plus xa is equal to Ktr mx plus a dot. Now, this is where Ktr represents the termination aspect. Now, in the reaction, m dot is the growing radical and xa may be the monomer initiator, solvent or any other substance, and x is the atom or species that is transferred. So, the rate of chain transfer reaction RTR, that is given by RTR is equal to KTR m dot xa, and that is the equation number 20. So, here this KTR is the rate constant for the chain transfer reaction. The new substrate radical A dot produced in the transfer reaction then adds to a monomer molecule to start a new chain. Now, here this A dot plus m is equal to m dot, and where the rate constant is Ki dash. Now, the chain transfer with the polymer formed may often lead to the branching and to an overall increase in number average molecule. Now, the effect of chain transfer on Rp, that is the rate of propagation, this depends on the value of the reinitiation rate constant, and that is Ki dot, this relative to the propagation rate constant Kp. Now, if we take a case that Ki dash is less than the rate constant of propagation, then Xa would have the role of an initiator or retarder rather than that of a chain transfer agent. So, the average degree of polymerization bar Xn now can be redefined as the ratio of the overall rate of polymerization Rp to the total rate of production of pairs of chain end, and this can be represented as the average degree of polymerization xn bar over Rp over FKD, concentration of I plus KTR m, that is m dot plus KTR is m dot, then S plus KTR m dot I. The first term in this denominator is also equal to RT over T, and the term KTR and KTRS and KTRS are the rate constant of the chain transfer reaction with monomer. This represents the solvent and initiator respectively. So, the chain transfer constant C for the transfer agent is defined as the ratio of the rate constant Ktr for the chain transfer reaction to the rate constant Kp for the propagation reaction. Now, the chain transfer constant for the monomer Cm, solvent Cs and initiator Ci, this can be represented as Cm is equal to Ktrm over Kp, Cs is equal to Ktrs over Kp, and Ci is equal to Ktri over Kp. This we can refer as equation number 21. Now, if we combine these equation 20 and 21, so we get 1 over bar xn is equal to F Kd initiator concentration over Rp plus Cm plus Cs S concentration of solvent, then concentration of monomer plus Ci concentration of initiator and concentration of monomer. This can be represented as equation number 22. So, which may also be expressed alternatively as 1 over xn bar xn is equal to Kt over Kp to the power 2 Rp m to the power 2 plus Cm plus Ci into concentration of I over concentration m plus Cs concentration of solvent over concentration of monomer. This can be represented as equation number 23. Now, there are certain substances which when present in the monomer or the polymerization system suppress the chain growth process to different degree. There may be a varying degree of suppression, usually by reacting with the initiating radicals or with chain radicals. They convert the radicals to non-radical species or inactive radicals or radicals too low in reactivity to undergo meaningful propagation. And such substances or radical scavengers are classified as inhibitors. Now, let us talk about the inhibition and retardation. Now, inhibitors, they effectively consume every radicals, whatever being generated in due course of time in the system, and completely suppress the polymerization and reduce the rate of polymerization substantially to zero. So, the introduction of inhibitor should be at appropriate time. So, on the other hand, the substance act not as effectively or much or less efficiently, so that both the rate of polymerization and the degree of polymerization are reduced quite miserably without completely halting the propagation process, and they are called as retarders. So, they reduce the rate of polymerization. Now, the inhibitors or retarders, they get consumed by reacting with the radicals during the inhibition or retardation process. The inhibition or total suppression of the polymerization continues till all the inhibitors molecules, they present a reaction mass or a system, they are get consumed. Now, example of typical inhibitors are benzoquinone, tertiary butyl catechol, and the stable free radical. Some of the typical examples of inhibitors are enlisted over here. Now, this particular figure shows the inhibition effect with 0.1% of benzoquinone. This is represented as in the curve 2, and the retardation effect in the presence of 0.5% nitrobenzene as a typical retarder, which you can see over here. The nitrobenzene 0.2% produces a complex behavior uh, showing the inhibition period followed by the polymerization at a rate lower than that of for the pure monomer, which is represented as here. So, you see that the inhibition and retardation effect in this particular plot which is plotted between the time and polymerization. Now, it is evident that the product arising from the reaction between the chain radical and nitrobenzene primarily behave as a retarder. Let us discuss about the kinetics of inhibition, because it is quite important. Again, it participates in the reaction mass. That is why it is very important to have discuss the kinetics of the inhibition. So, the kinetic of inhibition or the kinetic of polymerization for a system containing an inhibitor can be analyzed considering the reaction scheme. Now, here let us take this particular reaction Mn radical plus Z Kz Mn and Z dot, where Z represents an inhibitor molecule. Now, considering the sake of for the sake of simplicity, the reinitiation by the inhibitor radicals Z dot is negligible, and their termination does not lead to any regeneration of the original inhibitor molecule. Now, so the usual steady state assumption for the chain radical, this gives 2 kT m dot to the power 2 plus kz z m dot is equal to Ri. Let us say this equation number 14. Now, if we substitute the term Rp over Kp concentration on m for m dot, we get twice Kt over Kp to the power 2 into Rp concentration of m to the power 2 plus Kz, which we have already represented, K over Kp into Z concentration of monomer to rate of propagation is equal to rate of initiation, or twice Kt over Kp to the power 2 into Rp to the power 2 into m to the power 2 Cz into Z over rate of propagation is equal to rate of initiation. This can be represented as equation number 25. This is equation number 24. Now, uninhibited polymerization is given by Z is equal to 0 or almost equal to 0, or Kz is almost equal to 0, but when Z is not equal to 0 or Kz over Kp is greater than 1, the severe retardation or a typical case of inhibition results, and a normal bimolecular termination of chain radical receded to the insignificant values such as Kz over Kp into concentration of Z over concentration of M Rp Ri. This can be represented as equation number 26. Now, rate of propagation for strongly retarded or inhibited polymerization is dependent on the first power of rate of initiation. So, the rate constant ratio or the inhibitor constant, that is Kz over Kp, can also be deduced from the relative rates of reaction of the inhibitor and monomer with the chain radical. So, therefore, minus dm over dt, this can be equal to Kp into m and m radical. This can be represented as equation number 27, and minus dz over dt is equal to Kz Z into monomer radical. This can be represented as equation number 28. So, equation 26, if you recall this equation 26 readily follows, and we can rearrange this, gives to dz over dm is equal to kz over kp, z over m equal to cz z over m. Now, for if we take a case that Cz is greater than 1 for the polymerization or the monomer, consumption rate will be negligible for a significant concentration of the inhibitor or strong retarder with progressive consumption of Z during the inhibition period, the chain propagation assumes a competitive position only when concentration of Z reduces to a very low or insignificant values. So, equation 29, if we integrate, this can give you this particular value log Z over Z naught is equal to Cz log m over m naught. This can be represented as equation 30, where Z naught and m naught are the initial concentration of Z and m. Now, for an effective inhibitor, Cz being very large, it is evident from this particular equation that the initiator must almost be totally consumed before the monomer concentration drops measurably. Let us talk about the dead end effect in the addition polymerization. In radical induced vinyl polymerization, maximum possible conversion corresponding to the temperature of polymerization may be attained only if the initiator molecule do not get depleted during the process to below a minimum requirement to sustain the polymerization. This is quite obvious. Now, in the event of a limiting condition leading to large depletion or complete consumption of the initiator, now before maximum conversion of monomer to the polymer is accomplished. Now, this is known as the dead end phenomena. The dead end phenomena usually results in the limiting conversion of monomer to polymer consequent to depletion of initiator to such a low concentration as to render the half-life of kinetic chain and that of the initiator. Now, under the condition of say retardation, termination or due to the gel effect, it leads to sharp rise in the rate of polymerization, medium viscosity and a degree of polymerization. The pure dead end effect cannot be observed. Now, in case of dead end polymerization initiated by the thermal unimolecular decomposition of an initiator, let us say I, the rate of initiator depletion is given by minus di over dt, that is equal to kdi. On if we integrate this one, this can be given as I is equal to I naught exponential minus k dt. This can be given as equation 31. Now, where this I naught is the initial concentration of the initiator and the rate of polymerization Rp can be given by this particular equation. Rp is equal to minus dm over dt, that is equal to kp f kd I naught over kt to the power half m minus k dt over half. This can be given as equation number 32. So, if we arrange or rearrange, one can obtain minus dm over m is equal to kp f kd into I naught over kt to the power half e to the power minus k dt over 2 dt. This can be equation number 33. To more understandable, this is equation. Now, if we integrate this particular equation, we will get minus ln m over m naught, that is equal to 2 kp f I naught over kt kd to the power half into 1 minus e to the power minus k dt over half. This is equation number 34. Now, let m naught and m be the concentration of monomer at the start and after time t. Now, so the extent of conversion P from a monomer to polymer such can be represented as P is equal to m naught minus concentration of m over m naught. and 1 minus P can be given as concentration of M over M naught. So, the equation 34 which we derived previously, this can be represented as minus ln concentration of M over M naught is equal to minus ln 1 minus P is equal to 2 Kp F I naught Kt Kd to the power half 1 minus e to the power minus kdt over 2, and this is minus ln 1 minus p alpha into 1 minus e to the power minus kdt over 2. This can be represented as equation number 35. Now, at long times of reaction, let us say T is equal to alpha, the concentration of M and P attain the limiting value of M alpha and P alpha respectively, so that ln M alpha concentration of M naught is equal to minus ln 1 minus P alpha is equal to twice Kp F I naught over Kt Kd to the power half. This is equation number 36. So, if we combine the both the equation 35 and 36, so 35 and 36, then we will get ln 1 minus P over ln 1 minus P alpha. This is equal to 1 minus e to the power minus kdt over 2. This is equation number 37. Now, equation 37, this can be rearranged and expressed in a useful form if we take the logarithm, that is ln 1 minus P over ln 1 minus P alpha. This is equal to minus kdt over 2. This is equation number 38. Now, dead-end polymerization at several temperatures, which can be represented like such kind of a plot, like time versus the equation which we have previously derived, the rate constant of initiator decomposition reaction from the slope. Now, with the knowledge of Kp over Kt to the power half, which determined from the study of the degree of polymerization or the rate of polymerization, the parameter F over Kd may be experimentally determined. Therefore, the study of polymerization by the dead end technique permits evaluation of Kd and the efficiency of the initiator. So, dear friends, in this particular segment, we discussed about the various kinetic aspects of addition polymerization and discussed the kinetic parameters and rate of reactions for different cases, catalyzed, uncatalyzed, all these things. For your convenience, we have enlisted several references which you can use as per your need. Thank you very much.